Thank you very much. Thanks for having me. By default, any stay in Australia is always very nice. I like to be here. It's the fourth time for me. On the background, I have a very good cooperation with the people in Hobart, Utah. So we are doing a lot of ice sheet simulations there using Elmer. I will come to that later. So that's my relation background to Australia. If I'm a little bit slow, I'm still super jet lagged. Sometimes in the middle of the night for me, so bear with me. It's a good excuse because just I'm jet lagged and not slow by default. Anyways, CSC, if you wonder where I come from or where I work with, so is the non-profit company owned by Finnish Ministry of Education and the Finnish University. So the universities immediately directly have a saying in what we are doing. And yeah, naturally then the services are mainly provided for the Finnish academics. So I'm working there. By my accent, you might, which might resemble an action actor who lives in California now. Is not coincident. I'm from Austria. So, but I settled in Finland on my private background. So working there at CSC for more than 20 years now. I don't think I go through the further details, immediately jump in what we are doing since a while and doing quite good. So this is the development of all our machines up to the new era, which is not mentioned here, but shown in the next slide, which is Lumi, and which is also a reason that I'm here, because Lumi is basically the same system or a similar system as Photonics, just slightly bigger. And it's a consortium, so it's a European consortium shown here on the top line, but hosted in Finland and operated by CSC. So it's a HPE Cray with some CPU part, but also, and that's the main thing for the performance, a GPU part based on AMD Instinct GPUs. In its initial phase, it was number 3 on the top 500 list. Now I think it dropped to 7 or something. I didn't follow it up. Yeah, so these are the technical details of the machine, which I will not go through, but immediately jump into what we are here for today. It's about the Elmer finite element software. About the name, we had a discussion over lunch. The name Elmer is not deduced from children book elephants or Looney Tunes characters. It's just the shortage of the Finnish word for finite element solver, which I spare to pronounce here. So it's finite element based software for multiphysical problems, of which you can see a few here already. So we do everything from micro electromechanical devices seen up here. This was a case for a former Finnish cell phone manufacturer, Nokia, down to artery flow. This is an aneurysm here on the left side. I guess I have to use that pointer, right? Hope people online can see it. Even we have some particle model which should run here. I don't know, does the codec work? Apparently not, because of the Mac. Electrical machines. Where Elmer got big actually was in the initial phase. This was back in the late 90s. Elmer is that old. Perfect silicon crystal growth, which is a multiphysics problem, mechanics, fluid mechanics, and also thermodynamics. And of course, very prominently, Elmer ice here, a discretized version of the Antarctic ice sheet. this is quite an old poll, but I don't think things have changed that much. So we were asking people online on what they are preferentially applying Elmer to. So heat transfer, fluid mechanics, often in a combined way, solid mechanics, electromagnetics on the rise. That might be actually larger now. So electromagnetics is a very, very important field for Elmer. We even run a center of excellence on the national level, Finnish national level, within CSC, particular for electrical machine optimization. A little bit of quantum mechanics. You might have seen the Buckminster ball. So DFT is actually also implemented in Elmer, and something else, whatever it is, for some people, like exotic people like me, doing permafrost stuff and geoflows. I don't know how much we can go to a level of interactivity here with that much people online, so I'd rather skip that question. But maybe in the discussion, which I hope we have some room for, you can bring up what your favorite field of application might be. We can perhaps go more details. I already mentioned Elmer started in the 90s. What else is there to say on this slide? Basically, yeah, the major step we took, I think, was in 2008, where we decided to go open source, which was a gold decision for us. So Elmer is available under GPL version 2 for the whole part, and the Elmer library, which can be used as a solution engine, can also be called via LGPL. So thus saving people who want to do commercial application from the back infection of the GPL library. That's also a little bit outdated, but basically the spots show where Elmer is used. So of course, very prominently in Europe, but proudly so also in America and definitely also here in Australia. Though I think Tasmania should be lighting up here more, but perhaps there is a little bit inconsistency with the circle showing here. How is it planned? Do we interrupt for questions, or do I just carry on and people ask the questions? Yeah. Yeah, maybe we make breaks at some stage before I completely change the topic here. Okay, but let me carry on. So as I said, Elmer is open source, so we want to keep the spirit of open source and fairness, transparency. So everyone is welcome to contribute. We have a GitHub repository, and everyone is open to send in a pull request, which actually a lot of people do. I think Elmer is the most active Fortran code that there is on GitHub. What comes to pull requests, etc. As I learned from my colleague the other day. So Elmer can also be seen as an infrastructure, and particularly I think the gray circle on the lower right part is what makes us successful in some sense, that the Elmer is also intended to be run on HPC systems. So we invest quite a lot to port Elmer to new uprising platforms such as Lumi and Cetonix with the AMD GPUs. Already talked about the repository. So you see that there are quite a lot of branches. So a lot of developments are done in separate branches, and then generally we always merge to the main branch, which is the Devel branch. So we kind of have a, we don't do a lot of releases. So basically people should always refer to the current Devel branch or some commit on that one in order to get their stuff related if there is a problem, for instance. Yeah, I already said that Elmer is mainly written in Fortran, so the number crunching part particular. But we also use C and C++, for instance, to link to common libraries that there are. So we are not reinventing the wheel for a lot of things like the linear algebra. We use common libraries that there are around in the HPC world in particular, like Hypre, MUMPS, you name them. So we have some parts written in C. Generally, those interfaces are given in C. We have a very, and this is, I think, very important for the quality testing of the code. We have, I think these are outdated. I think we just exceeded 1,000 consistency tests for Elmer. So you can build Elmer and then immediately run C tests. Our building system is CMake, then run C test, check whether your installation is good to go or whether there are troubles. We have a lot of documentation online. I can show that later. Yeah, and the right-hand side is a little bit about the community. It's really hard to keep track in an open source code about the people using the code because you download it and you can stay anonymous. But we have a Windows binary which we maintain, and there we see about 20,000 downloads yearly of the Windows binary. If people use it, it's a different story, but that's basically the numbers we get. And we also give quite a lot of courses, particularly on the ICE side. So I'm still puzzled that 20 students travel somewhere to have 2 or 3 days of online face-to-face courses, but that's the case, at least in Europe. And we have several visits per year concerning Elmer. Okay, so that's a little bit about CSC and Elmer. History and status. Are there any questions, maybe online? I can't check the chat if there are. Else, I guess we can continue to the hopefully more interesting part. Okay. So Elmer, this is the structure of Elmer. So any basically multiphysics code has 3 phases. Let's call it phases in a workflow. One is the pre-processing part. The other is the analysis itself, and that's the key feature of Elmer. So it's the Elmer solver, and the rest is post-processing. And in the pre-processing part, and also in the post-processing, we heavily rely on existing open source solutions. Just one of them is shown here, that you, for instance, make your mesh in Gmesh. That's what we will do tomorrow. But there is also a software based on C++ called Elmer GUI. It's written with the Qt library. So if you have, for instance, more technical applications and have, for instance, some cut geometry, you can import it in Elmer GUI and let it mesh. There's NetGen inside Elmer GUI, and also a connection to Elmer Grid, which is a program that translates existing meshes. Like, for instance, if you have a mesh in ANSYS or COMSOL, you can import it and use it in Elmer straight away. So it's very compatible with other multiphysics tools. Then for the second phase, the analysis, of course, is the Elmer solver. That's the part mainly written in Fortran. That's where we are good at and where we constantly add new models. Elmer is built modular, so you have different problems here. For instance, in this example, you have a flow solution and a heat transfer solution, and you can combine them modularly. That means that also they are coupled sequentially. So you might have to iterate between those if there are nonlinearities, like, for instance, a temperature-dependent viscosity. You have to iterate between temperature solver and flow solver, but that's all taken care inside Elmer. So you can combine any of the physical models, and that there are a lot inside Elmer, as you want into one simulation. And I think that's one of the strengths of Elmer. And then for the output, we have a output visualization also included in Elmer GUI, so you can do the whole workflow if you want to inside Elmer GUI. But that's of course a trouble in HPC systems because running interactively on an HPC system is not so good. But for instance, if you have a Mac or a Windows machine or a Linux machine, you can install it and then run everything, smaller cases inside Elmer GUI, call the solver from there, and then do the post-processing. But generally, the workflow goes like that. You write out your files. They are written out in VTK format, and then use a open source, preferentially open source tool like ParaView to visualize them. We will go through that tomorrow also. But talking of Elmer GUI, so I already said it's based on the Qt library, which I recall also was mainly developed in Finland under the hood of Nokia. What else there is to say? I already said that card interface based on Open Cascade is there. So you can import your CAD files there and then have it meshed. And it writes out an XML-based definition of your case, which is, depending on how you see it, more or less human readable. Right, so it kind of masks all the process you should take manually, the manual labor, which you would need on a purely SK shell-based interface, which is possible to use, else you couldn't use it on HPC systems. Oh, okay, a glitch. You can use them inside Elmer GUI, but in a masked way. So you can click on boundaries and say, this is my boundary condition. You don't have to write the syntax. The syntax in Elmer, it's called solver input file, shortly for SIF. If you are into containers, that's a similar abbreviation like for singularity information file, I think, singularity containers, but we were first. We have that since '95 when containers didn't exist. So if I talk of the file, it's called, I usually say SIF. That's basically a ASCII-based syntax on telling Elmer what to do, what model to use, what mesh to use, what parallel paradigm to apply, etc. Right, and coming to the solver phase, you have the so-called Elmer solver. So that's really the number crunching part behind Elmer. So it does taking a certain physical model, the finite element assembly, and then calls the solver, whatever solver you're using, might be an external library like Hypre or Trilinos, and then creates the solution. This is about 95% of our development effort. And a disclaimer, Elmer is open source academic software, so don't expect, particularly the Elmer GUI, although it's a very nice software, to work like things that, for instance, ANSYS or COMSOL is providing. There's no way to maintain that level of support with 4 to 5 guys. That's what the headcount we have at CSC developing that software. So we focus on what we are good in, that's the numerical part, and we leave the other parts mainly to people who are much better in that, like, for instance, ParaView for the post-processing. One thing, and that might be interesting for people who want to try Elmer, but coming from commercial software like ANSYS, Abacus, FEEDUP, COMSOL. FEEDUP is quite outdated. Maybe you should take it from the list. There is a grid mesh translator called Elmer Grid. It's based on C, written by my colleague Peter Robak. And it is a very nice tool to import existing meshes and write out Elmer mesh format, which is a special format. There is, I think, no, actually there isn't. Gmesh also exports their own, what is that? their own mesh format, but Elmer Grid is able to read Gmesh. Gmesh is very important because it's an open source meshing tool. So it's heavily used by a lot of people in the scientific community, so also by us tomorrow. And Elmer Grid is also used then for parallel runs because Elmer is based on domain decomposition. And so you have to split your mesh in the amount of MPI tasks, so parallel tasks you're using on the computer. Was there a question somewhere?
Yes, there's a question on chat from Alexis, and he's asking, I saw an image of a bended beam by the fluid, so I guess you can simulate fluid structure interactions.
To some way, yes, you can. I don't know, maybe more specific. So what was the application? I didn't hear that acoustically.
So his question was, I saw an image of a bended beam by the fluid.
Bended beam, yes.
Yes, bended beam.
Yes, definitely that kind of interaction. So solid mechanics and fluid mechanics, we have that. Yes. That's
okay.
Yeah, thank you. Sorry, can you hear me?
Yes, I can hear you well. Hello.
Yeah, hello. So you said to an extent. So I'm wondering what is the sort of the limit, or what is the extent to simulate these fluid structure interactions? I'm not doing that kind of research anymore, but at some point we were thinking about this bending of structures, but also the structure really oscillating with the flow, etc. So that kind of things can be simulated with Elmer.
In principle, I say yes, but do you want to make time harmonic analysis of that, or what would be, or directly really real-time fluid structure interaction with the
fluttering, or I don't remember what is the, yeah, all the movement of
like
the
flapping wings or something like that.
Yeah.
But one thing I have to say, of course, we have fluid mechanics included, but there are, of course, tools based on finite volume, like open foam, that are much, much better in particular turbulent flows. So we have Reynolds averaged turbulence models and also some kind of, you would like to call it a large eddy system, which is, so it's variational multiscale method introduced by Tom Hugh, I think, some time ago. But of course, we are not specialized in fluid mechanics. So the problem then really has to be interactive. But yes, it's possible and to do also larger scale cases. One example, and I haven't shown that here, it's at the moment we are working on something which is called rapid rising glacial lake outburst floods, which arise in Iceland, where a pressured water pulse moves under a glacier, and ice basically can be described on that time scales. It's basically working on the time scale of the Maxwell time as a viscoelastic material. So, and this runs on several kilometer square problems. So we are doing the whole Vatnajökull ice cap there. So in terms of size, if you were asking for that, it should also be quite scalable. I have no idea what your particular application is, so it's hard to tell.
Yeah, no, but this is fine. This is a good response. Thanks.
Okay. Thanks for asking. Yes, please. Could you use the microphone, perhaps, that people can hear it?
I was wondering to us, have you tried the application of the Elmer on porous media as well, or not at all?
Yes, I come to that later. Yeah, I will tell about that. To show you a workflow now based on Elmer GUI, so that would be kind of a reading in a CAD geometry. That's how Elmer GUI looks like. Then asking to discretize the geometry. Then putting up the equations you want to solve. In that case, it would be apparently the stationary heat transfer equation. You also have to, of course, you have a set of predefined materials inside Elmer GUI. You can say just, I don't know, this piece of whatever it is, some pump or whatever is made of aluminium. Please use aluminium, then you get all the values. Basically, usually always based on SI units. Yeah. So you have to be aware that at this point of time, you're committing to a certain unit system. Generally speaking, Elmer is agnostic of unit systems. So it's in your responsibility to have consistent material parameters, mesh dimensions, you name it. So you're not locked into the SI system, but if you use material databases that are provided by Elmer, then it's SI. Yes, and then you set up the system. Elmer GUI will write the solver input, aka zip file, automatically, and then you can press the S button here on the top, and it will hopefully, if you correctly set up the system, there's also some check actually whether it's consistently set up, will give you a solution which you then can visualize either inside Elmer GUI or use PowerView. Everything is based on VTK files or whatever. I think Visit also accepts VTK files to be visualized. Right, so now we come to, maybe this also answers a little bit the question from before, what we have. So heat transfer, fluid mechanics with all the type of turbulence models. Also thin film flows. What's missing here is now recently we added a reduced dimensional Navier-Stokes equation for thin film flows that cannot be described by the pure Reynolds equations, but need acceleration terms in it. Structural mechanics, so we have general elasticity, which allows for larger deformations, and viscoelasticity based on finite elasticity implemented, and also reduced dimensional problems like plates and shells, which actually can be combined with the full dimensional problems. So for instance, if you have a beam that is in contact with a plate, you can divide those tasks to fully three-dimensional and reduced dimensional problem. Acoustics also was very strong, coming from the time when Nokia still was booming, and we helped to improve their microphones and speakers in the cell phones. Species transport, electromagnetics going very strong, already said. So electrical machine optimization, for instance. We have mesh, so we can do general arbitrary Lagrangian system. So you can choose whether you have a fixed in space mesh, a partly moving mesh, or a mesh that is really attached to, for instance, the fluid here moving, so complete Lagrangian formulation. We have level set method implemented, which, for instance, comes handy if you have a multi-phase flow, non-miscible multi-phase flow. Electrokinetics, we have had a phase where we did a lot of microfluidics. We have a few publications about that. For instance, Poisson-Boltzmann or simpler electrical dual layer models. Quantum mechanics is not really our strong side, but some time ago we had a DFT method implemented also in Elmer. And a particle tracer, which is not really finite element, so it's a semi-Lagrangian method, which is very handy for non-diffusional transport of species or whatever you want to check. Perhaps I make a short break. Are there any questions still concerning the available physical models?